Okay, so hello everyone. It's I'm glad to have this opportunity to have this talk today. The topic of my talk is the NMR pulse sequence basics and design principles. I'll just introduce the most uh, basic stuff about NMR sequence for those students who are interested in how NMR experiments work and how to write new pulse sequences. So, uh, as you know, there are quite a lot of different type of experiments. So those experiments are designed for different purposes. For example, if um, if you just want to record the chemical shift of a certain molecule to identify the molecule and to study their interactions, uh, like there is experiments like HSQC and HMQC. And for doing spectral assignment, uh, for for 2D spectra like HSQC, HMQC, you have to use some 3D experiments to do the assignment like HNCA, HNCCB. There are also experiments for relaxation measurement like R1, R2 experiments, CPMG experiments, and also for uh, you can also use run NMR experiments to solve a structure of certain molecules. For those for that purpose, the noisy experiments are most useful. Each type of experiment is implemented by a specific pulse sequence. When you run an experiment, you have to make sure uh, you have chosen the most suitable pulse sequence for the purpose of your experiment. But before into the details about pulse sequence, uh, I will first mention something about the basic theory of the MAR. So to describe how the experiment works, so there are several different, I think there are typically three uh, commonly used theoretical models to describe the MR experiments. The first one is the classic model. So this model is just based on the classical physics. And in this model, we have a magnetization vector, and we describe the motion of the magnetization vector during the experiment. So this model is most intuitive, but it only suitable for a single spin system. But in most cases, we have to deal with two spin system or more complicated spin system. So in that case, we have to use a more uh, some other uh, theoretical methods, like the density matrix. So the density matrix method is most accurate and is valid for all types of spin systems. But the main problem is the calculation based on density matrix is a little tedious. The physical picture is not quite intuitive. To so to help uh, so to help um, because the density matrix is not so easy for beginners. So usually we want to make some simplification based on density matrix. So that's how the product operator comes from. So product operator is just a simplification of density matrix. So the calculation based on product operator is much more simple and intuitive. And product operator can only be used for describing two spin and even larger spin system. Uh, so um, when we do the NMR experiments, we are starting uh, the nuclear spins. So as you know, because the nuclear spin is microscopic particles, so the description of nuclear spins, we have to use the Schrödinger equation to describe the system. So if we just have a single spin, then we can just use Schrödinger equation to describe. But in our NMR sample, we typically have a lot of molecules, so there are quite a lot of spins. Uh, so um, that means uh, we have to use density matrix to describe an ensemble of spins. So instead of a single spin, so the evolution of the ensemble of spin. So starting from Schrödinger equation, do the derivation based on the definition of density matrix, then we can get the Liouville-Newman equation, which describes the evolution of an ensemble of spin. The solution for Liouville-Newman equation is what it's not can be easy. It's not difficult to derive. So it's just like this equation. So according to the equation, if we know the initial state of the spin system, the density matrix and time zero, and we know this called Hamiltonian, then we can describe. Then we know how the system evolved. So that's what we want to calculate for any NMR experiment. So the density matrix size, so I think it's well defined. So usually we study we study spin 1/2 in most cases, like proton, carbon 13, nitrogen 15. Those all belong to spin 1/2. So if the system contains n spin 1/2, the matrix size would be 2 to the power of n multiplied by 2 to the power of n. Hamiltonian contains the energy information of the system, like chemical shift, pulse, radio frequency pulses, J couplings. In this equation, it's assumed that the Hamiltonian is time independent. So if we want to know the value of certain observable, so then we can calculate based on the density matrix according to this equation. So when we design the pulse sequence, so we usually need to follow the evolution of the density matrix during the pulse sequence. But in many cases, we can neglect relaxation effects. But in some cases, like for R1, like for relaxation measurement, CPMG or SES experiments, we cannot ignore those relaxation effects. We have to include that. So this equation, we haven't included the relaxation effect yet, but yeah, later I'll show how to add that. So first, let's look at this Hamiltonian. So as I mentioned, it said the Hamiltonian, it represents the energy of the whole system. So usually it contains several terms, like Zeeman term. Zeeman term comes from the energy of this due to the static magnetic field. Also, there's chemical shift, Hamiltonian, which describes the local chemical environment of the spin. The radio frequency pulses also have its own Hamiltonian. Also, it has J coupling, dipolar coupling, and also other terms. But I just mentioned in the previous equation, the Hamiltonian is time independent. But actually, in the system, not all Hamiltonians are time independent. At least there are certain terms like chemical shift, dipolar coupling. Those are actually time dependent, and the magnitude is modulated by molecular motions. But um, but if the Hamiltonian becomes time independent, the calculation would be more complicated. So in that case, what we usually do is to divide the time-dependent Hamiltonian into two parts. So one part is the time average value. So since this is time average Hamiltonian, this part would be time independent. The other the other part is time dependent, but we usually we think the second part, the major contribution is to relaxation effect. But the first part, the time independent part, we are more concerned about that. And when we calculate the evolution of the density matrix, we need to know the time independent part. So if the system, if in some case we need to take the relaxation effect into account, then the Liouville-Newman equation should be modified like this. So in this equation, we still have the first part, which is the commutator between Hamiltonian and density matrix, and we have introduced an additional part, which is called the relaxation operator. So this super operator, it defines the relaxation effect of the system. So this operator, it can be calculated based on like Redfield theory, based on the time-dependent component of the Hamiltonian. If the system has a conformation or chemical exchange effect, so those effects can also be included in this relaxation superoperator. But in this form, um, the solution is not very straightforward to obtain. So in order to solve this differential equation more easily, we can rewrite this top equation to this at the bottom. Here we just define this called Liouvillein, which just the meaning is just the commutator of the Hamiltonian. So if the differential equation is rewritten in this form, then the solution would become much simpler. So at least the formal solution is just the exponential of this Liouvillein plus the relaxation superoperator. Uh, so I have previously described two different ways to calculate. So the first equation is based on this von Neumann equation, and the second equation is this. So we will redefine a Liouvillein based on the Hamiltonian. So these two equations can be solved like calculation in two different space. So um, the Hilbert in the Hilbert space, which is simpler, the base is just the wave function. So each operator it applies on the wave function. The matrix size, so the basis has a matrix size of n times 1. Each operator has n times n. But in Liouville space, so that's where when we need to take relaxation effect into account. The basis is operator in Hilbert space, and the operator in Liouville space is usually called super operator since it applies on operator. The matrix size is much bigger than Hilbert space. If we have n spin 1/2, then the basis would be n squared times 1. Operator would be n squared times n squared. So in Liouville space, the matrix size becomes larger, so the calculation also is slower. But the major advantage is relaxation effects can be included more easily. Mm. So, but if relaxation effect is not uh, does not exist or it can be ignored, then you can either use Hilbert space or Liouville space to calculate. So the results from the two methods are totally equivalent. So here I'll just show a practical example to to show why the two methods are equivalent. So so first let's see how the calculation in Hilbert space. So this is the description for a single spin 1/2. So for a single spin 1/2, uh, the uh, the density matrix size would be 2 times 2, and Hamiltonian would be also 2 times 2. So when so if we want to calculate the evolution of density matrix, we need to calculate the commutator between Hamiltonian and the density matrix. So the commutator is calculated like this. So it's just a matrix multiplication, and then like this. Finally, we got the results in this red color matrix, which describes the evolution of density matrix. But if we want to go to the Liouville space, so first we need to construct a Liouvillein based on the commutator. So the definition is like this equation. So it's basically the Hamil the it should be called direct product between Hamiltonian identity operator. So based on this Hamiltonian, we got the Liouvillein, this 4x4 matrix. The density matrix, it now becomes a 4 by 1 vector instead of this 2 by 2 matrix. So if we need to calculate the evolution of density matrix, then we'll calculate this 4 by 4 matrix times this 4 by 1 vector. Finally, we get this red color results. So if you go back and compare this red color and this blue color, you'll see the numbers are totally identical. Only in one case it's a 2 by 2 matrix, and in this case it's a 4 by 1 vector. So this just means if you don't have relaxation effect, you can calculate either using this in this Hilbert space equation or Liouville space. It doesn't matter, you get the same results. But of course, if you want to calculate a bit faster, it's better to use this Hilbert space because the matrix size is smaller, so the calculation is faster. For any observable, so in Hilbert space or Liouville space, you should get identical results according to this equation. So then let's look at a few practical examples. For example, if you want to calculate the evolution of time evolution of a single spin system, and with relaxation effect, then you should write the differential equation like this. So this part, this 4 by 4 matrix, so it describes all the effect related to the evolution of system, like chemical shift, radio frequency pulses, and the relaxation effects. And if you want to study the chemical exchange effect for a single spin system, then the matrix would be larger. So because you need to introduce a second set of bases like X, Y, Z to represent the so-called excited states. And also you have this X, Y, Z component of the ground state magnetization. The chemical exchange effect, so it's represented by this off diagonal elements, like which is the exchange rate between ground and excited state. Mm. So these two examples are for single spin system, but sometimes we also need to deal with some more complicated spin system like two spin system. So the two spin system because there is uh, because usually it's a J coupled two spin system. It has J couplings. So the complete basis set will include totally 15 bases, and you just need to put in the number at certain position. And that's the way how to calculate the evolution of two-spin system. And so as you see, the density matrix, although it's most accurate, but sometimes it's just very tedious and not straightforward to to see how the calculation works. So that's why we need to introduce the product operator us uh, to help us to understand how the evolution of the system. So we have previously we introduced three different theoretical models like classic model, the density matrix, and product operator. If we just deal with a single spin system, a 1D experiment, then we can use either model and get the same result. For example, in classical model, uh, in this experiment, it's just a 90-degree pulse that rotates the magnetization from equilibrium z-axis to transverse plane, and then we start to collect the free induction decay. That's how the experiment works. So if we can also, of course, calculate the density matrix, although it's really not necessary to use density matrix to describe this simple experiment, but we can still do that. So at the beginning, we have this density matrix at equilibrium, a 90-degree pulse. After that, we get this form. And then during the free induction decay, the density matrix is like this. the product operator is also shown at the bottom. So the operator is just the response to density matrix in this. So let's just look at the relationship between the density matrix and product operator in more detail. If we have just a single spin system, then the single spin system we just have four operators: identity operator, X, Y, and Z component of magnetization. So the relationship between operator and density matrix is very clear. For J-coupled two-spin system, the complete basis would contain 16 terms. So the 16 terms is written in the here. So each operator, if you like, you can also write the operator to the corresponding density matrix. For example, here it shows the identity operator, the XY operator, X operator, and SX operator. So, uh, so these 16 components, usually it can be divided into several groups. For example, the in-phase magnetization is usually the IX, IY, SX, and SY. The Z magnetization is IZ, SZ, and so on. So the effect of chemical shift is to cause the interconversion between X and Y magnetization. You can think it the effect is to rotate along the Z axis, and also the pulse the role of the pulse is also to cause rotation, but the rotation axis depends on whether the pulse has phase X or Y. So if the pulse has phase X, then it will rotate Z magnetization to Y axis. So if that's a Y pulse, then you rotate along Y axis. You start from Z magnetization, you end up with X magnetization. For two-spin, in two-spin system, in most cases, it also has J couplings. So the effect of J coupling, because J coupling, the Hamiltonian for J coupling is this I2IZ SZ. So under the evolution of J coupling, if you start from X, you end up with 2IY SZ. Starting from IY, you end up with 2XSZ. The complete conversion time should equal to 1 over 2J, where J is just a J coupling value. Um, so in the coherence in for starting biomolecules, so usually we need to use 2D or 3D experiments. There are at least two spins to in the spin system. So um, so usually in most experiments we have to use some so-called coherence transfer scheme to transfer magnetization from one spin to another spin. For example, if you can transfer from proton in proton nitrogen HSQC experiments, the magnetization is transferred from proton to nitrogen and also can transfer back. So the coherence transfer, the method for coherence transfer, I think it mainly has these two different ways. One way is called inept, which is the abbreviation of this. And another way is to call cross-polarization. I think traditionally this inept is used more in liquid state NMR experiment and cross-polarization in solid state NMR experiments. But this is not quite absolute. In some cases, you can also do cross-polarization in liquid state NMR experiments. So the idea of inept is to apply simultaneous 180-degree pulses during a delay. And cross-polarization, you have to apply radio frequency field with equal B1 field on these two channels. And the transfer time is 1 over J, transfer between in-phase magnetizations. So although INAP is used more in liquid state NMR experiments, but cross-polarization also has some advantage for certain experiments. Here I show two examples where cross-polarization is more useful. One experiment is this called protein nitrogen CP HISQC experiment. So it's just an alternative version of HSQC, but instead of INAP, it uses cross-polarization to transfer from protein to nitrogen. The reason we want to do that is for certain system with fast solvent exchange. According to the simulation results, we see the CP-based magnetization transfer is much more efficient than INAP-based transfer. So that's why we prefer to use cross-polarization. The experimental results we can also confirm that to start a fast solvent exchange system using this CP HISQC experiment, we can still get a high resolution in N15 dimension. But if you use other experiment like the so fast HMQC, then the peak is much broadened. The resolution get much worse. Another application of cross-polarization is in this off-resonance R1 row experiment. And in this experiment, the cross-polarization transfer is used for selective excitation purpose. So in this cross-polarization are applied with relatively low power, which means only specific spins can be excited. So you can study one spin at one time. So that's about the pulse sequence basics. Then I'll talk something about the practical about how to about pulse sequence. So because now there are most users use Bruker to run the experiments. I'll just use Bruker software as an example. So in this software, the top spin, which is the Bruker, the software to operate. If you type the ASCD command, you enter the acquisition parameter interface. The first row is just the pulse sequence. You can also type pulse probe to set the pulse program. So if you want to look into some detail how the pulse sequence work, there are two different ways. The EDC pulse command will open the text editor to open this text editing interface. Also, if you want to look at the graphic interface, you tap SPDIS, then it will open the pulse program graphic display. Okay, so each pulse sequence it contains several basic components. So like including delays, pulses, and pulse field gradients. The broker, so the pulse program, if you want to edit that, you have to follow specific rules of the syntax. For example, each line of the pulse program it can only have one type among pulse delay or pulse field gradient, and you can have some comments after the semicolon and or place between this slash star. And also it supports several certain logic statement like if else statement, a loop statement. If you want to learn more detail about pulse sequence programming, so it's better to go through the manual of Broker because it's very difficult to complete completely describe all the syntax of the programming. So you always need to, if you something you don't know, you always need to go back and look in, search in this manual. So so the delays have in the pulse sequence, it has several different functions. For example, the certain delays are required for coherence transfer process. Like in NAP, you need to have uh, certain delay to let the magnetization transfer to happen. Also, there are delays required for chemical shift evolution for frequency labeling in indirect dimension and also in direct dimension. Uh, in relaxation experiment, you also need to have some delays. Usually, like for R1, R2 measurement, you have to measure a series experiments with different relaxation time. In noisy experiment, you also have a certain so-called mixing time to let the noisy effect to happen. Mm. And also there are delays required for specific operations in the pulse sequence. Like if you want to change the power or shift the carrier, you have to do those operations within certain delays. For example, if you this command is for this this is for uh, changing power on F1 channel, and this example is for changing the carrier position in F1 channel. Uh, so the second component is about pulses. So the pulses can be so there are pulses can be applied in many different ways, but you can typically you can classify pulses to several different categories. So one way of classify is based on it's called whether it's hard pulse or soft pulse. The hard pulse means the power of the pulse is close to the maximum available power on the probe. Usually the hard pulse is relatively short on the order of a microsecond. The soft pulse means the power of the pulse is much lower maximum available power on the probe. So typically it's on the order of a millisecond. So another way to classify is based on the shape, whether it's a rectangular pulse or shaped pulse. Rectangular pulse means the amplitude and phase remain constant during the pulse. And shaped pulse means either amplitude or phase change during the pulse. So in most pulse sequence that contains a series of 90 and 180-degree rectangular pulses, which are usually represented by narrow and wide bars in diagram, like here. Uh, okay, so each pulse it has several is defined by several parameters. Like the first one is the length of the pulse. In Bruker, the parameter P0 to P63 is used for define the length. Also, each pulse you need to define the phase, which is defined by pH0 to pH31. In most cases, the pulses have phase as multiples of 90 degree. The number 0, 1, 2, 3 represent 0, 90 degree, 180 degree, and 270 degree pulse. The channel is placed after the colon. Usually F2 and F2, F3 means proton, carbon, nitrogen channels. The power is also you need to set properly, which is defined by PL0 to PL63. So the power must be set before the application of the pulse, except for a shaped pulse. At the bottom, it shows the way how pulses are applied. The first example is a rectangular pulse, and second one is shaped pulse. For shaped pulse, it has several additional parameters, including like the pulse shape, the pulse offset, and the pulse phase alignment. Also, the power of the shaped pulse. So here I'll mention a little bit about the offset. So in order to understand how the offset works, you can actually in top spin there's a STDisk tool to you can edit and display the shape of the pulse. So the left side shows uh, the amplitude and phase of this eBird pulse at offset 0. So if you have a non-zero offset, for example, if that's uh, 1800, the amplitude is the same, but the phase now looks like it has a it's linearly changed component during the pulse. So if that's minus 1800, it's just the opposite direction. Phase is linearly changed. So this is the typical way to add offset to shape pulses. So you can it's called the laminar pulse. This method you can if you is described in this JMR paper. So if the offset is not zero, so when you apply that, you have to be careful about this SPOAL alignment, the phase alignment option. So let's still use this offset 1800 as an example. If the effect is to rotate from Z to Y axis, then this alignment number must be set to 1. Otherwise, you cannot get correct results. So instead, if the magnetization is rotated from XY plane to Z axis, then this parameter must be set to 0 to get the correct results. Uh, so this the simultaneous 180-degree pulse. So it's used in many cases. There are 3 different ways to apply. This L align means the line on the left side. Center is aligned to the center, and right is aligned to the right side. So usually we use this center aligned pulses most often. Uh, also, there's in the pulse sequence you have decoupling is quite commonly used. The decoupling is defined by this decoupling program CPD-PRG 1 to 8. So you have to define the power of the decoupling, the 90-degree pulse length under the decoupling power, and the method to decouple, like volts or Garp. So there are many different decoupling methods, but each has different methods have different properties. For example, Volt 16 have good decoupling property, but the bandwidth coverage is small. Garp has a larger bandwidth coverage, but its decoupling efficiency is worse. So depending on the application, you have to choose the suitable decoupling method. And at the bottom, it shows the way how to open turn on the decoupler and turn off the decoupler. The final, so the last part I'll mention is about the pulse field gradient. The pulse field gradient, the way how to apply is just to apply an additional B0 field, and the strength of this field is linearly change with sample position. That's how it works. There are So there are, I think, at least 3 different types can be classified to these 3 different groups. So the first group, the pulse field gradient, is to overcome the 180-degree pulse imperfection. So it usually forms a pair. So this pair of pulse field gradients are identical and before and after the 180-degree pulse. And for purge purpose, it's just a single gradient. And after the gradient, only key component magnetization survive, but it will kill all the other components. It's also the third type is for coherent selection. It's also a pair of gradients, but their strengths are different because they are applied on different nuclei. Okay, so finally, I will briefly mention a few examples. So I think there are the all the broker pulse sequence are now I think it's well is cataloged in this called broker pulse program catalog. You can find most the description of most pulse programs on the spectrometer. Here, because I'm most interested in studying proteins, I'll use HSQC as an example. So for HSQC experiment, actually there are a few quite few versions you can use. I'll start with the most simple version of protein nitrogen HSQC. So it's called HSQC F3PH. In this sequence, I think it even doesn't apply pulse field gradients. Actually, it only apply pulses. So so the way how the experiment works um in the theoretical part, I mentioned you can use the product operator to describe the evolution of system. So at the beginning, at equilibrium, we have the Hz, the Z magnetization on proton. Then the 90-degree pulse, we get Hy uh, product operator. After inept, we have this HyNZ. And during the T1 frequency labeling period, we have this, it becomes this. Then at the end, we have this red color term to detect. But this is not the only term at the end, actually. At the end, we also have this HYNX term, which is multi-quantum coherence. But remember, this multi-quantum coherence cannot be directly detected during FID detection period, so we can just throw it away. Mm, uh, so so but in 2D spectra we need to we need to do this quadrature detection to get the peak position properly. So the quadrature detection is usually we choose a pulse called quadrature pulse. We change the phase of the pulse, and well, then we get different results. So you can derive this by yourself as a practice. So if the phase of this pulse is shifted by 90 degree, at the end you will get this sine component. So then but previously we got this cosine component. Then by combining the cosine sine component, we get the complete spectrum. For HSQC, we also have a more complicated version, like this version, FHSQC F3 GPPH. It applies this water gate at the end. Also, it applies several gradient in the middle. But the final results are the same as this simple experiment. Now we look at a more complicated version, which is this. As you see, the sequence seems to look a little longer. You have to apply a few more pulses. Also, this is called enhanced sensitivity HSQC. The reason it is called enhanced sensitivity, uh, you can derive the product operator to understand why. So still starting from HC at the beginning, at the very end, we have two components, which are HX component and HY component. But see, the HX and HY, they are orthogonal to each other, so it's possible to separate them away. So in this experiment, the quadrature pulse is this in this red circle. But if the phase of the quadrature pulse is changed by 180 degrees, then at the end, you will get Hx cosine minus H1 sine. Instead of, but previously we got Hx cosine plus Hy sine. So now we have this plus minus. Now you can see it's possible to combine these two and to get each individual component to get this Hx cosine and Hy sine separately. In this way, achieves the quadrature detection. Okay. So this is just a simple proton nitrogen HSQC experiment. So based on the proton nitrogen HSQC, we can do quite a lot of additional experiments, like for example, for R1 uh, measurement, which measures the nitrogen 15 R1 rate, is just based on proton nitrogen HSQC. So the magnetization transfer pathway is to start from proton to nitrogen. During the uh, in this uh, in this time period, it will allow the NZ magnetization to relax, to evolve, and after this period, it will transfer back to proton. So in many cases, if you want to develop a new experiment, you don't need to start from the very you from the very beginning. Instead, the common way is to find some other sequence which are similar to what you want to run and use as template. And this example is the pulse sequence for running nitrogen 15 R1 row relaxation dispersion experiment. As you see, actually, except for the most center part for R1 row measurement period, the first the beginning part and the end part are almost identical to this pulse sequence for R1 measurement. So if you want to develop this new experiment, you can just start from a similar R1 experiment and modify this center part. That's the way how to write a new sequence. Okay, so yeah, I think that's all I want to talk today. So uh, if you want to, if there's anything not clear and you want to ask, I'm happy to answer your questions. Thanks.
Thank you, Dr. Yuwen. Really appreciate that talk. It was a good overview of a lot of those fundamentals. Everybody who like to ask questions, I'd like to point you towards the Q&A to pose those, and then I will pass them along to our speaker. I have a couple comments here from R. Wunderlich, who had to leave a little bit ago, but just wanted to pass on. Thanks for the very nice overview. And Marcus Cardoso also saying thank you very much for the nice presentation. While people are thinking about questions, I had a couple that came to mind. So you mentioned CP in solution, which is not often, I think, as you mentioned, what people think about. Very often it's inept in solution, CP in solids, and see more and more inept in solids as well, but seeing CP in solution, are there concerns about heating caused by the high pulse power and or just power limitations with solution probes, or is it actually much more feasible than your average solution spectroscopist might think?
Yes, I think that's one a major concern for solution MAR. The heating could be could be a problem, but I think it's not a big issue because in most cases the duration of CP is last say 10 milliseconds. The power you will need to apply is say on the order of 5 to 6 kilohertz. I think maybe on old probes maybe it's difficult, but I think on those new probes it's quite commonly you can easily run such power for for the duration of like say 10 milliseconds. I think it's quite common and don't cause too much problem. So, but maybe just the setup is a little more difficult, I think, because in inet you just have two pulses, single pulse to apply, but in CP you have to make sure the power on two channels are identical and the heating issue and yeah, people maybe people don't quite like it. Mm. Yeah, also the duration is longer because in CP a transfer between in-phase magnetizations. But in sometimes in that you don't really need to transfer from in phase to in phase. You can have only one half of the duration of CP. Then uh yeah. Mm.
I have a question here from Moshe, saying, what are the general rules and tips to determine / optimize the power of a gradient pulse?
You say the to optimize the pulse field gradient. Uh, Optimize, determine. Oh, okay. Mm, yeah, I think it's really yeah, it's a hard question. Because I also when I write new sequence, I also have this question. For example, in this HSQC experiment, there are quite a lot of you see there are quite a lot of gradients, but in many cases, the power is not unique. For example, for this G1 pulse, you can either apply as 50% or 10% or 70%. The results are very similar. They have these similar, you get similar results no matter which number you use. Mm. So yes, mm,
I guess to some extent,
uh,
could just be a matter of just seeing from experimental trial and error, are you getting the result out of your gradient?
yes, trial and error is important because I remember when I do that, in some cases, if the strings is not set up, is not suitable, then the water suppression becomes very bad in the sequence. Because one major concern about when you study biomolecules is the water suppression. Your samples in water. I think the reason to apply most gradients uh, is to get a clean spectra. To means you want to suppress water better. So if the power somehow, mm, uh, for example, this G1, you change from like 30% to 10%, maybe the water suppression somehow becomes worse. But it's hard to explain why that happens. You have to go to a spectrometer and try. Mm. That's
Kind of,
my experience.
kind of in the same way that you would calibrate a 90-degree pulse. You kind of start from somewhere close to where you know from previous that it might work, and then hone in on
Mm.
an optimal value.
Yes.
Yeah, so that kind of bridges well into a question from Nahum, saying, hi from Colombia. Just want to say thanks for your presentation, and also had a question about how to calibrate the gradient pulses, which I think you may have covered a little bit right there, where you kind of are looking for the water signal and seeing if the water signal is being well suppressed or not.
Yeah. Mm.
All right, and then Barbara saying, many thanks for the nice overview. Little comment. The syntax is changing with the electronics and software versions. The Pulse program manual showed here is a bit outdated. And for example, the SPF notation is now deprecated in the most recent versions of Topspin. So I was curious if this is actually something that I've noticed at times too, that the syntax has changed a little bit.
Yes.
Kind of off of
I also
that,
noticed.
are there things that you wish would be brought back or added in the future? As I'm sure there are at least one or two people from Brooker who might see or hear this.
I think so far, mm, yeah, I think so far it already supports a lot of uh different syntax. Yeah, There's something missing. Uh, yeah, I don't
Not so
quite
much.
remember.
That's fair.
Mm.
All right, we also have question from Gazelle. When using fast sequences, what is the technical limit for what is the minimum time for a pulse sequence? And thank you.
You mean fast technical limit? Mm, minimum. Uh, yeah, I think depending on, I forgot. Uh, I think depending on whether the sequence it has some. Yeah, I really actually I don't know this version of fast sequence is used. But if the sequence it doesn't apply, say the decoupling during acquisition, I think you can set very short delays. Because if that doesn't apply decoupling during acquisition, then I think even the D1 is set to zero, the duty cycle is still not very high. But if you apply decoupling, say nitrogen 15 decoupling during acquisition, then you have to be careful. It cannot be too short. But I don't remember which version. I remember there are some versions, don't maybe that's a chosen version. Yeah, which doesn't do the decoupling. Then mm, you can use as short as you want. Mm.
I guess to some extent it's limited by the actual polarization transfers to some extent. If you have to just have enough time for the actual experiment to happen to a certain extent. If you are no longer really worried about the duty cycle.
Mm.
But yeah, so our next question from Marcus, saying concerning the same issue of power of the gradient field, can it have a minimum power below which the xi dephasing is too small?
Yes, I think that of course that there should be a lower limit. Uh, uh, if you set very small power, then I think it almost has no effect that could happen. But actually, what's the minimum? I think I have to we have to do some calculation. Uh, because I think if we go back to this slide, because the effect of the pulse field gradient is to cause a local linearly changed B0 field so from the bottom to from top to bottom, the sample experience different local field. So if the strength is so weak that from the bottom to top to bottom, it doesn't even sample was 360 degree. I would think that then the it's too weak. But either but the total effect is you have to consider the strength of the field and the duration of the gradient. So if that's a very weak gradient, if you apply for a long enough duration, then it may still accumulate this phase difference from top to the bottom. But if the gradient is too long, it's not quite practical. Typically, the gradient is I remember it's on the order of say 1 millisecond or half millisecond. It's very rare to apply very long, but unless if you want to measure say the translation diffusion or some other application. But I think you have to do some rigorous calculation to to see what's the minimum.
If I remember properly, different probes also have different gradient maximums for their gradient channels at times. And so it might also be a
Yes,
function.
you have to. Yes. I think the power at 100%, you only have to use some standard sample to calibrate. I think it's different from one probe to another.
Yeah. All right. We also have from Raul, thank you from India, and from Juan Carlos, thank you very much. Very nice presentation. And Gazelle responding with a thank you. And yes, they are using decoupling, and sometimes when it is too short, it does refuse to work. And so he thanks you for a very nice overview. And Kalindi also saying thank you. And YH, I assume, initials saying glad to see that we're back online again.